Hello everyone, welcome to you all in the next lecture of electrostatics. Often there are both an easy way and a hard way to do a job. The easy way may involve nothing more than using the right tools. In physics, an important tool for simplifying problem is the symmetry properties of systems, and Gauss law is a part of the key to use symmetry consideration to simplify electric field calculations. So today's topic is Gauss theorem, but before discussing the Gauss theorem, we need to know what is the electric flux. So, the electric flux is basically defined as the number of electric field lines passing through a given area normally. Like if I am having a cubical box and the charge is plus charges inside this box. So as we know that for the positive charge, electric field is away from the charge, and if I will represent the electric field with the help of electric field vectors, the direction of electric field will be like this. So as you can see that from all the surfaces of this cube, the field lines or electric field is going away, outward. In that case, we say that flux is outward from this cube. Since the electric field lines are passing from this surface, so there is a flux associated with that, and since the field is going away from the box, then the field is outward. It means flux is a outward flux. On the other hand, if I will consider a negative charge inside the same box, then we know that field lines will enter this box, because for negative charge electric fields is towards the charge, and in that case, since the field lines are entering inside this box, we will say that the electric flux is inward flux. Now if I will take a box that is completely empty and there is no charge inside, so the electric field lines will not enter as well as they will not go out of this box since there is no charge, and we will say that the flux associated with this box is 0. So if a body, or if a cubical body or any kind of body contains a positive charge inside it, we will say that it will be having an outward flux. On the other hand, if we are having a negative charge inside the body, we will say that the body is having a inward flux, and in case of no charge inside the body, there is no flux. Now we will study that how to calculate the electric flux associated with a surface or a body. So as I told you that electric flux is defined as the number of lines passing normally through a given surface. So let us consider a situation where there is a uniform electric field in a region and I am having a surface. The plane of this surface is normal to uniform electric field. If I will draw an area vector that is always normal to the surface, normally outwards, so electric field vector and the area vector both are in the same direction. I am taking the magnitude of area as A and the electric field magnitude as E. So for such kind of situations, the electric flux is represented by phi, and E stands for electric flux, that is simply the product of magnitude of electric field and the magnitude of area. But this condition is only valid when your electric field vector and the area vector are parallel to each other, and as it is the product of two scalar quantities, electric flux is a scalar quantity. On the other hand, if I will take my surface as it is and say that electric field is something like this. Now if I will draw a normal to the surface, it will come in this direction. Now since electric field and area vector both are not in the same direction, basically they are not parallel to each other, and let me choose this angle as theta. So to get these two in the same direction, what we will do, I will find out the component of this electric field along this area vector, and it will be E cos theta. Now this E cos theta and the area vector both are in the same direction, so with the help of this definition we can find out electric flux as E cos theta multiplied by A. In other words, we can also write it as E perpendicular A, since it is the component that is perpendicular to the surface here. So this is the second case when both the electric field and area vector are not in the same direction. Now in both the cases I have taken the uniform electric field. Now what will happen if the field is not uniform, or what will happen if the area is not a standard area? In that case, suppose that it is a place where the electric field is not uniform, and I have to calculate the flux associated with this surface. So what I will do, first of all, I will take a small area, say my area is ds, and it is the area vector. Similarly, I will find out the electric field at this point, and let it is the direction of electric field, and these two are having theta angle between them. So for this small surface, the electric flux will be, as per this definition, it will be E ds cos theta, just like this one. As you know that E ds cos theta can also be written as E dot ds, because the product of two vectors with a dot is E ds cos theta. It is simply the definition of the dot product. So this is the flux associated with this small area. Now if I want to calculate the total flux through this surface, what I need to do is I have to integrate this small flux over the surface, and we will get integral E dot ds. So whenever electric field is not uniform or the surface area is not a standard shape, we can use this formula. Sometimes what happens, the surface is enclosed surface, or it is a bounded surface, it is closed surface. So for that case, we may write this equation as closed integral of E dot ds. This tells us that the surface chosen by us is a closed surface. It is not an open surface like this. The closed surface may be a cylinder, it may be a spherical shell, spherical body. Now we will discuss Gauss' theorem. Just like the Coulomb's law gives the relationship between the charge and the electric field, Gauss' law provides a different way to express the relationship between electric charge and electric field. The Gauss' law states that total flux through any closed surface. Here, closed surface means a surface enclosing a definite volume. So, the total flux, that may be an inward flux, that may be an outward flux, the total flux through a closed surface is proportional to the 1 by epsilon naught times the charge enclosed within that surface, or we can say that it is numerically enclosed charge divided by epsilon naught. This is the statement of Gauss' theorem. Now we will prove this statement of Gauss' theorem with a very simple example. Consider there is a point charge that is placed at the center of this spherical shell. Now, since this charge is enclosed by this spherical shell, so I can apply the Gauss theorem, because it tells that there must be a closed surface. Here, my closed surface is a spherical shell. So for that, consider there is a small portion over here. So this area vector is always normal to the surface. Now, for positive charge, the field is always away from the charge, and here electric field and the area vector both are in the same direction. So the flux through this small area will be E ds. Now, if I need to find out the flux through this total surface, because the field lines will come out from this surface from all the directions, so the net flux will be the integration of this small flux over this spherical surface, and this is going to be E ds. Let me choose the radius of this spherical cell as r. So the field I can calculate at this point, and if you will see that this magnitude of electric field will remain constant throughout the surface, since all the points of this spherical cell are at the same distance r. So the formula for the point charge electric field is 1 by 4 pi epsilon naught q by r square, and this magnitude of electric field is same everywhere on the surface of this spherical shell, and this is ds. This whole term is a constant, so this is going to be 1 by 4 pi epsilon naught closed integral. I will write closed integral here since it is a closed surface, and this is ds. And just look this term. This is the integration of this small surface. It means the integration will provide me the total surface area of this spherical shell, and we know that total surface area of a spherical shell, this is q by r square, will also be here 4 pi r square. So if you can see, r square 4 pi, and the left term is q by epsilon naught. So my net flux through this spherical surface is 1 by epsilon naught times the net charge inside this body. It is very clear from this equation that the flux from this surface is not depending on the radius. I will give you an example of this. For an example, suppose this is a point charge, and I will take a spherical surface taking this charge as a center, and the radius is r. And once again I will consider another spherical surface of the area of this. Now, since the magnitude of charge is fixed, so it will originate a fixed number of electric field lines, and that electric field lines which will pass through the spherical surface of radius r is exactly same as the number of lines that will come out from this spherical surface. Since the number of lines that are passing from this r radius spherical cell and this 2r spherical radius cell is same, it means the flux associated with these two spherical cells remains same, and that is what the Gauss theorem states, that it doesn't depend on the radius. Doesn't matter what is the radius of the spherical shell or the surface surrounded by the charge, the flux will only depend on the net amount of the charge inside the closed surface. In the previous topic, we have seen that how we can calculate the flux associated with the spherical cell using Gauss theorem. Now, the Gauss theorem is not applicable for the symmetrical surface or the spherical surface, just like a sphere only, but it also holds good for any kind of closed surface. If I will take a charge and the surface that encloses the charge is not symmetrical, it is not a spherical shape, it is not a cylindrical shape, it is some kind of random shape, in that case also the Gauss theorem is applicable. That means the flux will be charge divided by the epsilon naught. if I will take a negative charge inside that surface or inside another surface, the electric flux will be minus q divided by epsilon naught, because you know that for positive charge the flux is outward flux, and for the negative charge the electric flux is an inward flux. So Gauss theorem is applicable for all kind of surfaces that surrounds a charge. Sometimes the charge is inside the surface and outside the surface also. For an example, we will see an example where there is a surface. Inside this surface there are two charges. This is one plus q1, another charge is minus q2, and the third charge is lying outside this surface. This is q3. So for this surface, or how to solve this situation, just consider one more thing before solving this, that suppose my charge is outside this surface. So if you will see about the electric field lines, it will be like this. So the number of field lines that will enter from this surface will be exactly same as the number of electric field lines that will be leaving this surface. So in that case, from the left surface the electric field lines are entering. Entering means it is a inward flux, and from this surface the same number of electric field lines are leaving the surface, means it is an outward flux. So what is the amount of the entering flux is same as the amount of flux that is leaving the surface. So in that case the net flux from this body will be 0, since the net flux is not going out and going inside the surface. So if a charge is outside the surface, the net flux from that body due to this charge will always be 0. So by this example we can see that the flux that will be associated with this charge will be 0 for this surface. So only the charges that are inside the body will contribute the flux, and as the definition says that it is the enclosed charges. Now I am having two enclosed charges, q1 and q2, and we know the additive nature of charge. So the net charge will be q1 minus q2. This is the net charge enclosed by the surface divided by epsilon naught. So by this way we can find out the flux associated with surface, where some charges are inside the surface and some charges are outside the surface. Now since Gauss theorem provides the simplest tool to find out the electric field due to several charge distribution, now we will discuss the applications of Gauss theorem, with the help of which we can find out the electric field due to several charge distribution in the simplest way. So first of all, I am taking a charged wire, and that is an infinitely long charged wire. Since it is an infinitely long charged wire, so we know that it is not a discrete charge system, it is a continuous charge system, and we need to find out the electric field due to this wire at this point P, that is at a distance of r. So to apply the Gauss theorem, first of all we need to find out the enclosed surface, because once our charge is not enclosed we cannot apply the Gauss theorem. So for that I will just take a cylindrical Gaussian surface, since it resembles with the cylindrical nature of the wire. Now this is my Gaussian surface, and let the length of this cylinder is L. So we can define the charge density over here. Let me take this charge inside this cylindrical surface is Q, and the length of the wire is L. So the charge divided by length, and that is the charge density. It means we can find out the charge inside this spherical surface, and that will be lambda times the length. Now as you can see that the flux, electric flux, may come out from this surface, from this circular surface, top one, and the bottom one, circular surface. So I will consider the three sections, the upper one circular section, the lower one circular section and the curved section. So for positive charge, the electric field, as you know, is always away from the charge. Let me this electric field as E1. For this surface, the field is away, this is E2, and the same here for the positive charge, the electric field will be away. Now as we know that to calculate the electric flux, we need the area vector. So for that surface, area vector is ds1 vector. For this, the area vector will be always normal to the surface, this is ds2, and here it will be ds3. And it is very important here that the angle between E and ds here is 90 degree. So if I want to calculate the total flux, it will be the flux associated for this surface, flux associated with top circular surface, and the flux associated with bottom circular surface. Now we will apply the formula. This is E ds1 cos 0, because these two are parallel. For this surface, we will write E2 ds2 cos 90, as the angle between E and ds is 90, and plus for this surface it will be E3 ds3 cos 90. The value of cos 90 is 0. It means there will be no flux associated from this top circular surface and this bottom circular surface. So these two terms will be 0. And we know that Gauss' theorem tells that the flux is nothing but the enclosed charge divided by epsilon naught. Let me take this electric field as common, and this will be ds1. The value of cos 0 is 1. Now we know that the charge enclosed from this cylindrical surface is lambda times L. So we will put the value of charge here as lambda L divided by epsilon naught E closed in or integral ds1. This ds1 is the curved surface of my cylinder, and we know that the total curved surface of the cylinder is nothing but 2 pi RL. This is lambda L by epsilon naught. L will cancel out from here, and the electric field will be, on rearranging, 1 by 2 pi epsilon naught lambda by R. It is very clear from this electric field that there is no term that contains L. It means it is not the electric field due to this finite length only, it is the electric field due to whole wire, as this expression doesn't contain the length L. We can also write it as 1 by 4 pi epsilon naught twice of lambda by R. And this is the electric field due to infinitely long straight wire at a distance of R. Here I am taking R, this is capital R. So it is very clear that field decreases on going away from the charge. Now we will discuss another application of Gauss' theorem, and that is the electric field due to a charge sheet. For an example, suppose I am having a sheet of infinite dimension, and this is a charge sheet, and we need to find out the electric field due to this charge sheet at a point that is just outside the surface of the sheet. So consider my point is just outside the sheet. So from the symmetry, what we will do, we will take another point that is just behind the sheet. This is for this calculation purpose. So my point is just outside the sheet, and I have taken another point that is just behind the sheet. So to calculate the electric field due to sheet, we have to use the Gauss theorem, and that tells that we need a Gaussian surface here. So just like the previous example, we will take a cylindrical surface here also. Find out the electric field. And this is my point. So, as we have already discussed that for a cylindrical surface, the flux can be calculated for three different surfaces: this circular surface, and this whole one, curved surface. So just consider that here the electric field is E for positive charge, it is away from the charge. For this point, the same electric field will be here also, because I have taken the point that is just in front of shield and just behind the shield. So due to symmetry, the field will be same in magnitude at both the points. Now for this curved surface, let us assume that electric field is even here. So we will take a small area ds1 here, thus ds2 here, and this is small area ds3 here. So for this ds3, the area vector is normal, for this area vector is normal, and for this area vector is normal to the surface. So as you can see that here the electric field and the area vector both are perpendicular to each other, so the flux associated with that surface is going to be 0, just like the previous one. And the area vector and the fields both are in the same direction for these two surfaces, so I will calculate the net flux as the sum of flux from this surface and the sum of flux from this surface, because the flux from this surface is 0. So for this surface and that surface, the flux will be E ds1 cos 0 plus E ds2 cos. See, cos 0 is 1, so we can write it as E integral ds1 plus E integral ds2. Now the area of these two circular surface will be same, and let me take the whole area of this circular portion as A. So this area is A and this will also be A, so we can write these two terms as A, and from Gauss' theorem we can write flux as enclosed charge divided by epsilon naught EA and EA. Now to find the flux that is associated, that is inside this circular surface, we need to define the surface charge density, and that is nothing but charge divided by area, and this area will also be A. So the charge inside this one is sigma times A, so we will use the value here. The charge enclosed is sigma A by epsilon naught. This is equal to 2 times EA. A will cancel out, and electric field is going to be sigma by 2 epsilon naught. And once again, here is, since A cancelled out, it means it is not the electric field due to this area, it is the electric field due to whole sheet. So this is the electric field using Gauss' theorem due to a infinite dimension sheet. So far we have discussed the electric field due to a charged sheet. Now suppose I am having a thick conductor here. If I will give some charge to this, the charge will be distributed here on the surfaces only, because we know that the charge cannot be inside a conductor, and if this conductor is uniform, then the surface charge density of both the surfaces will be same, that is sigma. Now I need to find out the electric field due to this thick conductor. So I can find out the field at 3 different points. The first point, that is at the right side of the conductor, the second point, that is inside the conductor, and the third one, a point P3, that is in the left of the conductor. Now as we know that there will be no charge inside the conductor, so what we can do, we can take these two surfaces of the conductor as a thin sheet, and if these two can be taken as a thin sheet, so for this sheet at this point the field will be away, and its value is going to be sigma by 2 epsilon naught, as we have discussed earlier. Similarly, it is also a thin sheet of the positive charge, and for positive charge the field due to this sheet will also be sigma by 2 epsilon naught. So the net electric field at this point is going to be sigma by 2 epsilon naught plus sigma by 2 epsilon naught, and that is sigma by epsilon naught. So for a conductor, we will just assume that my conductor is composed of 2 thin sheets. The same we can do here also. For this sheet, the electric field will be E, and for this surface the electric field will also be E, that is in magnitude, and the direction for both the charges will be away from the charge. And if we can add these two, we are going to get the same result here, that is net electric field is sigma by epsilon. It means in front of the conductor and at the back of the conductor, at a point that is just outside the conductor, the electric field is sigma by epsilon naught. Now this point is important. Inside the conductor, for this sheet, the electric field is going to be away, but for this sheet, the electric field will be away from this sheet, since both will produce the same amount of electric field, but they are in the opposite direction, and this results the zero electric field inside the conductor. It means for a thick conductor there is no electric field inside the conductor, but there is a field outside the conductor, left side in the right hand side also. Now we will see another application of Gauss theorem, and we will find out the electric field due to a charged shell. So just look at this. Consider I am having a spherical shell that is uniformly charged with charge Q. Let me take the center of this cell as O and the radius of this cell as R. Now I need to find out the electric field for this cell. So we will find out the electric field first at a point P, that is outside the cell, and the distance of this point from this center is small. I will write it like this. So to apply the Gauss theorem, first of all we need a Gaussian surface. With this symmetry we can draw a Gaussian surface, a spherical surface, taking the center as the center of the charged shell. So this is my spherical Gaussian surface, and to calculate flux we need a small area first of all. So this is my small area, and area vector will be normally outwards. Since the shell is having a positive charge, so for that positive charge the electric field is definitely away from the charge. So these two are in the same direction, and by the Gauss theorem we can write it like closed integral E dot ds. This is closed integral E ds cos 0. Since both are parallel to each other, so angle between them is 0. I can write flux is enclosed charge divided by epsilon naught. E I will take common, and this is closed integral ds. Now, as we know that this is the charge inside the Gaussian surface. My complete cell is inside the Gaussian surface. So inside the Gaussian surface the net charge is Q. So I will write it as Q divided by epsilon naught, and that is E, and this ds will give me nothing but the area of this Gaussian surface, and the cell is having area 4 pi r square. So my electric field comes out to be 1 by 4 pi epsilon naught Q by r square, and this is very interesting that it is also the electric field due to a point charge. It means if I will take electric field into cell at a point that is outside the cell behaves just like its charge is placed at its origin, and the formula is just similar to the electric field due to a point charge. So this is the electric field at a point outside the cell. Now if I need to find the electric field on the surface of the cell, so if I will shift it here, my small r will be equal to capital R. So my point shifts from here to here, and this distance reduces from r to radius of the cell, and if I will place it here, I will get 1 by 4 pi epsilon naught Q by capital R square, and this is the maximum field due to this cell. Now there is one more space that is inside the cell, and we need to find out the electric field inside this. So for that, consider this is a point P dash. Once again, to apply the Gauss theorem we need the Gaussian surface. So I will take a Gaussian surface of this radius. Now, if I will apply the Gauss theorem, it tells that it is enclosed charge divided by epsilon naught. Left side we can write as closed integral E dot ds, and that is equal to, now just see that inside this Gaussian surface there is no charge. And since there is no charge inside this Gaussian surface, we will put the value of enclosed charge as 0 and the right side will be 0. Now in the left hand side, it is the product of electric field and the surface area. If you can see clearly, this Gaussian surface has some surface area. It means ds is not going to be 0. So if the product of two quantities is 0, one is not 0, then it will be the other quantity that is going to be 0. It means that there is no electric field inside the charged cell. We can just show this graphically also. For an example, say it is my charged cell and this is the center. So inside this cell there is no electric field, but at the surface electric field is maximum, and if we will move away from the cell, the electric field decreases as 1 by r square, or decreases in the same way as the electric field due to point charge lasts. This is going to be like this. So this is the graphical representation of electric field due to a charged cell.